Good morning, friends. Yesterday we were discussing about more details about the plates and shells. In that, more about the plates. And yesterday I have already discussed you the criteria on which the degrees of freedom are associated. In that, I have already defined you C2, C1, and C0 continuity elements. And out of that, we have started with the most important element called rectangular element with 12 degrees of freedom. That is what it has got 4 nodes with 3 degrees of freedom per node, which are nothing but W, rho W by dou X. The degree of freedom are W and dou W by dou X and dou W by dou Y. 2 slopes and 1 deflection are going to be considered. Yesterday I have already told you the polynomial contains the following terms, like let us say W is equal to alpha 1 plus alpha 2 X, alpha 3 Y plus alpha 4 X square, alpha 5 XY plus alpha 6 Y square, alpha 7 X cube, alpha 8 X square Y and alpha 9 XY square plus alpha 10 Y cube, alpha 11 X cube Y plus alpha 12 X Y cube. We have neglected 3 important terms. So therefore, these are the 12 terms which are going to be included in this. This, in short, we can write it as P into alpha, where P is nothing but the vector 1x y x square xy y square x cube x square y x y square y cube, then x cube y plus x y cube. Okay, these are the terms which are going to be there. And if you take the dou w by, there's a dou x out of this, all the x terms will go, which we call it as the theta x, which is the slope alpha 3 plus alpha 5 x 2 alpha 6 y plus alpha 8 x square plus 2 alpha 9 xy I think this is wrong, because alpha 3 is not containing this. This is yes, I think we'll have different one. See, dou w by dou x, which is our theta x, it is 1, anyway, no 1, because there is no x is there. Then alpha 2 plus 2 alpha 4x plus alpha 5y, alpha 6 is not there, 3 alpha 7 x square plus 2 alpha 8 xy plus alpha 9 y square, this will not be there, plus 3 alpha 11 x square y plus alpha 12 y cube. Okay, this is about dou w by dou x into this. So if I take dou w by dou y, which is the theta y, if again this alpha 1 is not there, so directly I will get alpha 3 plus alpha 5x plus 2 alpha 6 y plus alpha 8 x square alpha at xy plus 2 alpha 9 xy 3 alpha 10 y square alpha 11 x cube plus alpha 12 x 3 alpha 12 x y square. So these are the, what you can say, slopes, the two slopes. These the degrees of freedom are expressed in terms of the polynomials what has been taken. So out of that we are going to take these terms now. There are totally 12 terms. So if you substitute these values, let us quickly substitute these values as xi, yi, z, wi into that. See what we were going to get this. Substituting xi, yi for nodes 1, 2, 3, 4. If we substitute that, what we get here, W1 theta x1 theta x2 or theta y1, W2 theta x2 theta y2, W3 theta x3 theta y3, W4 theta x4 theta y4. This is going to be the relation, and here obviously this, since there are 12, so this matrix is going to be 12 by 12 matrix. This one is going to be a 12 by 12 matrix, and here we are going to get all the terms, these alpha 1, alpha 2, alpha 3, alpha 4 up to alpha 12. We are going to get this. All this can be expressed as delta E is equal to G inverse of, I can say, alphas. You can call this equation as a 7. And if you want the alphas, obviously you have to take the G inverse of this. Inverse of G, you have to take that. Then only you have to get that. Now the displacement within the element, the displacement W within the element can be expressed as W equal to P alpha, and as such alpha itself is known, P G inverse of delta E. This you can call it as equation number 8. This you can call it as equation number 9. Okay. So this is about the displacement within the element is concerned. And the deflection field for any point can be expressed. The displacement field for any point can be expressed in terms of the shape functions, natural coordinates. You can find normalized coordinates you can use. I equal to 1 to 4 Ni 1 Wi plus summation I equal to 1 to 4 Ni 2 theta xi plus summation I equal to 1 to 4 Ni 3 theta yi. This is equation number 10, where these shape functions Ni, for example 1, what is this contains? In terms of natural coordinate, zeta and eta, how to express this one? It is 1 by 8, 1 plus zeta I, zeta, 1 plus eta I, eta, 2 plus zeta I, zeta I, eta I, eta I, minus zeta square, make it zeta square. To call this as 10a, this is 10b. Similarly, Ni for the second one, for the slopes, minus b by 8, Ni, 1 plus theta I, 1 plus theta I square, 1 minus theta I. This is 10c, correct? Similarly, Ni for the third one, shape function for the third slope, minus a by 8, zeta I, 1 plus zeta I square, 1 minus zeta I, 1 plus zeta I, zeta. You can call it as 10 by t, and these are the dimensions product, zeta and eta end product. So here, if I want the zeta to the x minus xc upon a, and eta y minus yc upon b. Xc and yc are the coordinate of the center of the element. Coordinates of the center of the element. Okay. See, there is a big set of equations where I cannot go on dictating orally. I'll have to write it. Most of the time, I will be forced to see my back only. But unfortunately, the equations are so big, they have to be written. Unless it is written, it is very difficult for you to understand what I have written there. Okay, these are the three shape functions used for finding the overall deflection or the displacement at a given point. Finally, the W. What is W now? Is going to be N delta E. This is what the deflection is. Now let us go to strain component. Once we know the deflection, strain E is given by kappa x, kappa y, kappa xy. This we have seen in the last class. This is nothing but minus dou square W by dou x square minus dou square W by dou y square minus 2 times dou square W upon dou x dou y. Okay, so this is again going to be given like this, minus 2 alpha 4. If you take the differentiation of that polynomial, minus 6a alpha 7x minus 2 alpha 8y minus 6 alpha 11 xy. Similarly here, minus 2 alpha 6 minus 2 alpha 9x minus alpha 10y minus 6 alpha 12 xy. Lastly, minus 2 alpha 5 minus 4 alpha 8x minus 4 alpha 9y minus 6 alpha 11 x square minus 6 12 y square. Okay, so this is going to be the strain components which are going to be expressed in this particular fashion. So as you know, strain is always the product of B into Q, that is strain displacement matrix into the displacement vector. So from this I can now rewrite this, the whole thing, which is equal to Q alpha, which is equal to Q alpha is nothing but G inverse of delta, which we have already done, which is equal to this product, we call it as B into delta E. This is similar to the Q vector, that is displacement vector, whatever it is. So therefore, where B, the element displacement vector, is nothing but Q into G inverse. If you write in which, okay, this equation is 15, this is our 11th equation, these are our 12, 13, 14, you can write that. Okay, this is our 12th, this is our 14th, 13th, and this is our 14th, and this is our 15th. So here, what is this Q? Q can be written as 0, 0, 0, 0, 0, 0, 0, 0, 0, minus 2, 0, 0, 0, minus 2, 0, 2, 0, 0, minus 6, minus 2y, 0, 0, minus 6xy, 0. This is 0, 0, 0 minus 4x, minus 2x, minus 4y, minus 6y, 0, 0 minus 6x square, minus 6xy, minus 6y square. See, this is our equation number 16, what you can write this. So this is the Q, and after multiplying this Q with the G inverse, what you get is the B matrix. So let me quickly write how exactly we can write the strain displacement matrix for this. So therefore, from equation 10, B can be used minus 1 upon A square, dou square Ni upon dou zeta square, minus 1 upon B square, dou square Ni upon dou eta square, minus 2 upon AB, dou square Ni upon dou zeta dou eta. You can write it. This is going to be a kind of equation 17, you can call it. So this is the, what you call it as the strain displacement matrix. Because we have the steps, like for example, we start with the deflection, then we write about the strain components, and strain component is expressed as B into Q, where we write the B matrix first, and now we enter into how to find out the element stiffness matrix. So therefore, the stiffness matrix, relating to relating to mx, my, so 3 moments, and mxy with the nodal displacement w, theta x and theta y. If we want to write, this will be Ke, elemental stiffness matrix, double integral B transpose C D dx dy, or you can write it in terms of G transpose, okay, yeah, this is a G. You can write this. Here you can write Q transpose CQ dx dy into bracket G inverse. In natural coordinates, if you want to write, that is G, d zeta and d eta, in terms of that, Ke is written -1 to +1, -1 to +1, B transpose C B into determinant of J. This is, of course, I'll write it as determinant of J into d zeta d eta. This is equation number 19. This equation is 18, and this is 17 already we have taken. Okay, so this is about what you call it as the element stiffness matrix, where determinant of J is nothing but the Jacobian determinant, and it is equal to the product AB, because it is half of the area of the triangle. So naturally 2A into 2B will be the into half, that is the area of the triangle. So it will be 2AB. Half of that is nothing but the area determinant of J. Like that we have to find out that. See, if you look at the equation number 8, if the generalized coordinates from equation 18, if they are used for stiffness calculation, the terms within the integration signs can be multiplied and integrated explicitly. Please remember that. An explicit expression for the stiffness matrix has been evaluated for the purpose of orthotropic plate. This is what we have done is for isotropic plate. If it is used for orthotropic plate, Mr. Jankiewicz has done a lot of analysis on orthotropic plate. Please refer to that book. You will get more details about the analysis of orthotropic plate as such. And if you look at the equation number 19, which is in terms of the natural coordinates, the integration has to be carried out numerically. That I have already told you. D zeta, d eta, and determinant of J, when it comes, it has to be done, you can say, numerically. Of course, here it may be noted that the shape function expression is always containing 4th order terms. Okay, and hence the second order differentiation, the terms in B matrix, they contain second order terms. And the stiffness matrix, which has the form of B transpose CB, will contain 4th order terms in zeta and eta. Hence, we need 3/3 Gaussian integration to get the exact solution of what is the order? 2n minus 1th order. We have to go for 2n minus 1th order. Now, we will write down some expressions for the lateral loads, both surface and body type. We are assuming, they are assumed to act at the middle surface, and the consistent load vector for the distributed load on the surface is now, we will be writing that. Let us write the consistent load vector when we consider the distributed load which is acting on that. So this is given by Fe is equal to, okay, Fe, you can say element modal vector. It is double integration n transpose xs dx dy, or you can also write F can be written as Fe If you convert this into natural coordinates, it will be the integration sign will change from dl, the 0 to L to -1 to +1. This will get n transpose xs determinant of j into d zeta d eta. You will get that one. Okay. So this also can be written as G inverse transpose double integration P transpose xs dx dy. Okay, this equation you can call it as 20. And if you have a concentrated load, see for example you have concentrated load WC, let us say WC, it acts at the center of the plate, or whose coordinates are XC and YC. This acts on a plate. For example, if you have a plate here, and if this is your XC and YC, and if the load is acting here at WC, how to take into account this load vector into the equation that is given by FC is equal to N transpose WC. Okay, this is what we can write. So this is about what you can say about the 12-degree rectangular element. See, this particular element has got certain deficiency. Whenever it is required to map with all the given degrees of freedom and as far as the slopes are concerned, it should conform to all the requirements. Suppose if it is not conforming, then we call it as non-conforming element. That is what we are going to now check that. See, always you remember that determinate and indeterminate equations what we write. Determinate means what? When you have certain number of unknowns. That is, if you have n number of, you can say, unknowns, we should have n number of equations. Suppose if I require 4 unknowns, then I should have 4 equations to solve it. Then only I can be able to get unique solutions for all the 4 unknown variables. But by chance, if you have number of variables are more compared to the number of equations known, then definitely you will not have unique solution. This is called non-conformity. So this is exactly what is happening in this 12-loaded, you can say, rectangular plate. So that is exactly what is that. We'll just check and we will see that. Okay. It's called non-conformity of the elements. Non-conformity of the element. Let me make a small sketch here. Here I will be considering 2 adjacent elements which are having a common edge. Like for example, if I take this edge, this is being the 0. Okay, you call this as 1 and 2 as the 2 nodes which are there on this. This is element number 1. This is element number 2, you can say. Okay, this is our x-axis. So obviously both of y is 0 for both of them. Here y1 and y2 are 0 here for both of them. Only x1 is there. So this will take y plane in this downward direction. If I show this, this is my first conforming 4 degrees of freedoms, W1 and W2. If I write the slope at W by Wx and dou W by dou x at node 2, these are going to perfectly get that. But when it comes to the other, that is 1 and 2, when you write this is W1 and W2, this will be there, this will be there. Ideally speaking, it should be there, but there is going to be non-conformity of the element. So therefore, this will come like this. So that is dou W by dou y1 here and dou w by dou y2. See, look at this. There is no unique solution as far as the second slope is concerned. As far as the first slope is concerned, there is always a uniqueness is there. So now, if you look, I am now presently taking two elements which are adjacent to each other. They are having the common edge 1, 2, and they are aligning with the x-axis. Therefore, the y terms are 0. So if you set y equal to 0 in your deflection equation, your modified w will become now alpha 1 plus alpha 2 x plus alpha 4 x square plus alpha 7 x cube. Only these are the terms what you will get, and automatically if I want theta y, this is theta w upon dou x, this is theta x, alpha 2 plus 2 alpha 4 alpha 4x plus 3 alpha 7 x square. And if you want theta y, which is dou w by dou y, other terms are coming, alpha 3 plus alpha 5x plus alpha 8 x square plus alpha 11 x cube. Okay. So once these terms are set 0, these are the things which are going to be there. So the conditions available are what are the conditions available are now see here at both node 1 and node 2. First, deflection W1 at 1 and W1 at node 2, they have to be the same. So let us call this as equation number 1. W2 at 1 and W2 at 2, again they have to be same. This is the second condition. Then dou W by dou X at 1 must be equal to dou W2 upon dou W1 upon dou X at 2. So this is our 3. Similarly, dou W2 upon dou X at 1 must be equal to dou W2 upon dou X at 2. See, these are all the 4 important parameters. The next 2, that is dou W by dou Y at 1 must be equal to dou W1 upon dou Y at 2. This is our fifth equation. Dou W2 upon dou Y at 1 must be equal to dou W2 upon dou Y at 2. This is your next last equation. So if you look at these 6 equations, out of that 1, 2, 3, 4, if you look at that, there are 4 equations in 4 unknowns. Okay. If you look at this, what are these 4 unknowns? We will write now equations. I think, I will write here equations 1, 2, 3, and 4. Okay, these, if you look at these first 4 equations, the unknowns are alpha 1, alpha 2, alpha 4, and alpha 7. So hence, there are 4 equations and 4 unknowns. So obviously, the solutions of these are unique. So therefore, we always get uniquely, they are all uniquely determined. These are all uniquely determined. Whereas when you go to the next equation, that is, in other words, it is nothing but W and dou W by dou X. That is they satisfy the requirement of uniqueness. Because this is the meaning of this is, these are satisfying the requirement of the uniqueness. This is what you can see, 4 equations and that. Whereas when it comes to the last 2 equations, equations are 2, but unknowns are 4. So what are those? So if you take equation 5 and 6, Okay, 5 and 6. Only two equations. What are the unknowns? Alpha 3, alpha 5, alpha 8 and alpha 11. See, that's why it is indeterminate. We cannot solve four unknowns with only two equations. So, there may be number of possibilities which will find out the value of those. So, therefore, there is no uniqueness. So, dou W by dou Y, no uniqueness. This is called nonconformity. So this is one of them. Disadvantage of this element. Later on, the other authors have added one more degree of freedom to this, and they have tried to overcome this problem of nonconformity in this type of elements. Now, with this, let us quickly move to another type of element which is called as a rectangular plate element with 16 degrees of freedom. Rectangular plate with 16 degrees of freedom. Okay, from 12, we are adding another one more, you can say, degree of freedom, that is dou square W upon. See, Mr. Bogner, who has done this? Who? Bogner, Smith, and Fox. These people have considered another, what you can say, degree of freedom to this, and they have added one more. So with that, they have tried to overcome the non-conformity faced in 12 degrees of freedom element. So now it leads to totally 60 degrees of freedom. That is per node. What are the now per node? What are the degree of freedom? Per node, W is there. Dou W by dou X is there. Dou W by dou Y is there. Now in addition, dou square W by dou X dou Y. So this is 4 degree of freedom, and totally 4 into 4. 4 nodes into 4, totally 16 degree of freedom are going to be there for this particular element like this. So naturally the generalized displacement contains now the terms. We have to check the W terms. How many W? 16 terms are there. Obviously we need 16 constants. So therefore let us quickly write all the terms in the deflection W in the form of a polynomial. What is the polynomial now? W will now become alpha 1. That is always constant for geometric isotropy. Alpha 2x, alpha 3 y plus alpha 4 x square plus alpha 5 xy, alpha 6 y square, alpha 7 x cube, alpha 8 x square y, alpha 9 x y square, alpha 10 y cube, alpha 11 x cube. Plus alpha 12 x square y square plus alpha 13 x y cube, alpha 14 x cube y square plus alpha 15 x square y cube plus alpha 16 x cube y cube. Okay. So these are the, you can say, terms which are there in this total equation. See, he has considered, it may be noted that to get the geometric isotropy, Bogner have considered the terms appearing in the product. He has considered the product 1 plus x square plus x cube, 1 plus y square plus I cube. He has considered this. Okay. And one can proceed on the lines explained for 12 degrees of freedom. Element 2, assemble P, G, F and B matrix and then evaluate the stiffness matrix. The size of of course, the element stiffness matrix is now what is that? Since 16 degrees of freedom are associated with the element, then the size of the element stiffness matrix is going to be of 16 by 16. Okay. So this we are trying to write all this in terms of W. In eta term, I equal to 1 to 4 Fi 1 Wi Fi 2 theta xi Fi 3 theta yi plus Fi 4th theta xi y. This is 23, right? Where theta x, this what is theta xy is nothing but dou square W upon dou x dou y. These Fi1, Fi2, Fi3 and Fi4, these are called Hermitian functions. Okay, these are not ordinary functions, these are called Hermitian shape functions. We call it in beams. If you remember, we have used these Hermitian shape functions. Here also they are called Hermitian shape functions. Of course, there are totally n. If you want to define totally, there are 16, you can say, shape functions are going to be defined here. So we will not be going in detail about all these things. So let us quickly write down this. Okay, with this there are totally 16 number of degrees of freedom are associated, and we will go for that. Okay. Now with this, these are all called Timoshenko type of plates, elements. Now we are going to another one of the very, very important element called as Windell's plate element. Windell. Windell's plate element. Okay, I'll just quickly take the sketch of this. This is called as XZ plane. This is X, okay, and this is your Z. This is your Y plane. The rotation is in the XZ plane. That is, this is nothing but dou W by dou X. Dou W by dou X. And this is the rotation theta X. See, out of this, these are the three normals. See, one is dotted and one this. So first let us say this is what is this? This is normal before deformation. And the second one is normal after deformation. And this is the assumed deformation. See, now let us quickly find out the difference between the earlier plate element what we have studied and this Windell plate theory what we have studied here. Of course, Windell theory is nothing but the extension of Timoshenko theory what we have studied and for the analysis of the plates. Here, as we have seen in the case of continuity elements C2, C1, C0, I had specially made one mention at the C0 element, that is the W and theta x and theta y are decoupled. So we don't write that theta x is equal to dou W by dou x, theta y equal to dou W by dou y. We no more relate theta x and W, and therefore we keep them independent. So this is will help us in simple for formalizing the equations and all that. So therefore, Windell is one of the very important assumptions. See, he has got some three important assumptions. Let us quickly note down that. First, this is nothing but a C0 element. Please remember, this is the C0 element. First point to be noted down here is he has rotation and the lateral deflections are decoupled. Rotation and lateral deflections both are decoupled. That is exactly what I wanted to tell you. And next is shear deformations are considered. The moment you consider that, shear deformation will come into picture, shear energy will be taken into account. Shear deformation is considered. Okay. This is another very important point to be noted. Here we are going to study four-noded quadrilateral element, which is a linear element. And if you want a higher order element, eight-noded quadrilateral element. This is not okay. Yeah, this is the quadrilateral element only. And eight-noded quadratic plate bending element. Okay, these are the two things we are going to look into this type. See, one of the very important points yes, you have to remember always is assumptions made by Windell. These are the very, very important points what you will be asked in examinations. What he has assumed, first very important thing is, he assumed that the lateral deflections, that is W, are going to be very, very small. That is, he is considering thin plate with small deflections always. And the most important, second important is stresses normal to the bed surfaces are always negligible. This is the second important thing he is making. Then he gives up Kirchhoff's assumption that the plate normal to the bed surface remain plane even after bending. Instead of that, what he assumes is normal to the plate mid surface before deformation remains straight, but not necessarily normal to its after the deformation. So let us quickly note down, because these are important. I'll write down all the three assumptions here now. Let us quickly note down Windell's assumptions. Okay, first, what is the first assumption? Tell me. First assumption is the lateral deflections its lateral deflections W. Deflections W are small. That is why a thin plate with small deflections, you can say. And the second one is stresses normal to the mid surface. Stresses normal to the mid surface are negligible. Okay. Then the third one, that is what I told you. It's another, he just bypasses the assumption made by the Kirchhoff, and he says that the normal to the plate mid surface normal to the plate mid surface before deformation remains straight. But not necessary normal to it, after deformation. You can see that in the figure, the normal is no more remaining as this one. So therefore, we can say these are the three important assumptions made by Windell. What you can say about this. Okay. Now let us quickly go for the analysis part. Whatever is possible today, we'll do it, and then tomorrow we'll complete this plate, and then we'll go for the introduction of the shell elements. Okay. Now theta x, what we have seen in the figure, is the final rotation in x direction. It is the final rotation in x direction. That is theta x is equal to dou w by dou x. This is nothing but minus average shear strain in the x direction. This is given like this. So therefore, that is theta x is given by dou w by dou x minus phi x. This is the strain. And similarly, theta y is given dou w by dou x minus phi y. You can call this as equation 26 and equation 27. And the three parameters theta x, theta y are related by our shape functions over the summation I equal to 1 to n. Here n is the number of nodes in the element. Ni 0 0 0 ni 0 0 0 ni. Wi theta xi, theta yi. This is 25, where n is the number of nodes in the elements. If 4 nodes are there, n equal to 4. Okay, this is the equation relates the corresponding values of the deflections at a given point x and y, and these are going to be there. And already you have studied in 4-noded quadrilateral element, n1 is given by what? 1 minus zeta, 1 minus eta by 4, and n2 is given by 1 plus zeta, 1 minus eta by 4, n3 is given by 1 plus zeta, 1 plus eta by 4, and n4 is given by 1 minus zeta, 1 plus eta upon 4. In the similar sense, for quadratic element, if you go for quadratic element, n will be 8, no? There are 8 nodes. N will be 8 elements. So then, automatically we get the coordinates as x and y, summation ni xi, summation ni yi is equal to summation I is equal to 1 to 8, or you write n in general, ni 0 0 ni xi yi. This is the 28th equation you are going to get this. So these are the expressions for what you can say developed for these things, and in the next tomorrow's class we will discuss about more about the strain components. See, there are of course 2 types of strains are going to be there. One is called a flexural strain. How to get the flexural strain, and then the shear strain, how to get that, and then we will find out the stress resultant curvature and all the other details. We will get that, and then we will go to more details about that. Okay, I think with this we will stop.